Hello, everybody. How are you doing? Sorry about the little delay, a little bit of fun we were just having with the editor, but we do have Jess here. Jess, you here?
Hi, everyone.
Yay, Jess is here. Okay, so we're going to be we're back for C. We're going to do C as an additional language. This is topic 9. I did not have a chance to update the syllabus, but on the website, but I did update the syllabus in my notes. So I'm going to work off the notes. We have basically one topic tonight. Jess seems to think C is easy, and she's just
When did
been
I say that?
she's been flying through the lessons and going, this stuff, this memory management, that's a piece of cake. I do this stuff all day. So I think to get a real appreciation for what's going on with memory management, we're going to be doing some fun tasks that we discussed last week. So the subject for today is really kind of a split between what we had in topic 8 in the previous syllabus. So last week we really focused on binary IO and we did a little bit with pointers. So this week we're going to go pointer happy because it's time to get to, Jess kept asking, how do I dynamically allocate memory? And she wanted to use that bracket notation and just leave it brackets and say, oh, well, the C compiler work. And that works at declaration time, but it does not work after declaration time. So in order to do that, we had a very brief introduction to a function that, do you remember what it was, Jess?
Malloc?
Yes, that's exactly
Okay.
it. The dynamic
Yep.
memory allocator. And I said, and one of the questions I asked was, well, how do you implement this? Because at some point someone had to implement malloc. So for tonight, we are going to implement our own malloc. Told you it'd be fun. So this is going to be, we're going to go for a very simple allocator, the kind of simple allocator that I mentioned last week. So this is, here we are. We have Jess on the screen. We're in topic 9. And Strophium says, gross. How do I flag not safe for work? Yes, there's only one topic on the board. Bring your own allocator. So we're gonna make our own allocator. We are going to understand dynamic memory in ways we have never understood dynamic memory before. So this part is really the focus. We're gonna go for the simplest possible allocator, which is the one that I briefly mentioned last week, which is the stack base. And by the way, that 20 that I rolled, that was a real 20. That the camera was on, you all saw it. So that I really rolled that 20. So I feel like that 20, this 20 here is going to help Jess tonight because malloc is, oh boy, weighted. If it was weighted, it was weighted at the factory. I got this die straight. Okay, so this will be fun. So we're going to do a stack-based allocator. And so let's get into our coding screen here. All right. We're going to talk a little bit about, I'm not going to just throw her straight into the deep end and go, all right, go implement malloc. We're going to help a little bit, right? And chat's going to be helpful because Strophium really wants this to work. All right. So we're going to do, oh wait, we're not doing topic 8. We're doing topic 9. Oh man, why do I have this super crappy brush? So I just did an OS upgrade and my brushes are all over the place. This stuff is tell me I lost my, yeah, that's my streaming pen. All right, I don't know why this is going to be so. Is that still readable or is it just impossible?
It's a little hard. I mean, I think I
right.
can make it out, but I'd worry about some folks on stream.
Yeah, you know what? Let's figure out, because I just upgraded, and of course, whenever you upgrade your operating system, wonderful things happen. So I had some nice streaming brushes that just don't want to, no, I don't want to rename the group. I want to fix the brush. All right, come on. All right, edit brush settings. Sorry, everybody. let's take a moment now and deal with it. Okay, so brush radius, we'll just bump the radius up and that should be good. All right, hopefully, yeah, okay, that's a little bit better. I don't know where my normal brush went. I'll go debug it later. All right, so let's do that. Yeah, all right, now we're crazy brush. All right, so great. We have brushes, we have painting, we have topic 9. So this is C as an additional language, and we are going to be building our own allocator. So let's do it. Now, I don't know why there's such tremendous lag on this pen. All right, I'll worry about that later.
It looks nice. It looks nice to me.
Okay,
So
well, if it looks
I
good
can
to
read
you,
it.
that's
We're good.
the most important thing. So we really only have one thing to do. We have to build an allocator. And how do we build an allocator? Well, the interface was already defined. So we're going to be implementing word for word the same interface that we have on malloc. And actually, let me put that over here, because what is the actual interface for malloc? When you call malloc, it gives you back your favorite new data type.
A void pointer?
Yes.
Okay, yes, it was a total guess because we were talking about this earlier.
And when we're allocating memory, what do we have to tell it?
How much?
Yeah, how much? All right, so that's a size thing. So we're going to go with a size t, and it has something like how much. All right, and don't worry about this size t, because this used to be an int, but it's going to be aligned for the platform, and it's a standard thing. But anyway, we'll use size t. It's just basically a number, but it's going to be a positive number because you don't have negative sizes. Okay, and we had a matching call when we were done with the memory. What do we do to it?
Free.
Yeah, and what do we have to give free? Free takes
Probably
only
the
one
same
parameter.
thing. The size.
It doesn't take a size. It takes a what?
The pointer.
Yeah,
that malloc returns.
Exactly.
So it knows like what to free.
Yeah, we have to tell it what to free, and so that's going to be passed in as a void pointer to be nice and generic. And this is really free what. Okay, and it doesn't return anything that we're really concerned with. So this is our interface. It's well defined. Malloc has to allocate memory and chop it up and hand it back to the program dynamically, and free has to deal with cleaning it up. So this dishes it out, this cleans it up. Okay, any questions on the interface?
I don't think so.
It's time tested, it's mother approved, it's been around for ages. Okay, so actually malloc is absolutely not mother approved. I think if my mother was a programmer, she would not be happy about the state of affairs. Okay, so great. Well, how can we build this? And by the way, keep in mind, you're going to be coding this. So we're going to want to build this as simple as possible. So first of all, what do we need to do? Like at a high level, what are we doing? I mean, we're taking in keep in mind, we're taking in a size and we're returning a chunk of memory.
Mm-hmm.
So in order to be able to dish out memory, what do we need? We need memory.
Memory. It's like a trick question.
Yeah, no, totally not a trick question. So we need a nice chunk of memory. All right, and this is going to be our heap of memory, as it were. Now I'm going to put that in quotes because it's not actually on the heap. It's going to be on the stack tonight. But we're going to get to the difference of that in a little bit. We're just going to refer to this because in the original sense of what the heap meant, this was just a heap of memory. So. Okay. Great. Now, what we need to do is as we're mallocing, we're asking for different sizes. So say the first person comes along and asks for malloc of, 8 bytes. Okay, so we need to go and say, well, this was the start, right? We need to know where we started. This is the end. When we get to here, we are out of memory. Oh, no. So this is bad. We don't want to get here because bad things are going to happen. So we want to sort of stay, but we don't really control that when we're writing the allocator. We have to just deal with whatever the user requests from C. So all right, we allocate. Our first call is we malloc 8. So we're going to take this little chunk here. We're going to say this is 8 bytes wide, and we're going to give you that back. We need to give back a pointer to the start of it. So here you go. And then the next dude comes along and says, I want to malloc 4. And so we're going to say, fine, I got your 4. Take this and advance it by 4, so it'll be half the size. And here you go. You're good to go. That's your chunk of memory. And the next one comes along and says, I want to malloc something that's the size of a planet, because we learned about that the other day. And we had a nice struct of struct planet, and this ended up being 14 bytes after we packed it. So the compiler knows that, so we don't have to worry about it. And it's basically going to say, yeah, here we're just going to advance this 14. We're going to take this chunk, and we're going to give it back to you. So there you go. There's your 14. So bookkeeping-wise, what do I have to kind of keep in mind? I have to watch where I am, right? Mm-hmm. It's really important to kind of know like what the furthest chunk is. Now, when free comes along and starts having to deal with this situation, so we take this thing and we want to free it, and then we take this thing and we want to free it, and we take this thing and we want to free it, what do we have to do? We have to say that this is no longer in use, right? So this memory is now available to be reallocated if we want. Mm-hmm. And that's on the first free call. So that's the free call that corresponds to this malloc. And then on the next one, when we take this thing, now we don't know what order they're going to be deallocated in. They might not be deallocated in the same order that they were allocated in, right? This one might get removed first. And then, well, let's assume the 8 did, and then the second one was this, 14 byte thing. So then this one was left back, but I still have this memory here in the middle. So if somebody comes along asking for this whole chunk, I can't take it from here because that's not contiguous. I only have this this part and this part. So we're not going to worry about this case of reallocating memory. Like I said, that's a good allocator. We're not going to try to build a good allocator because it has to deal with this problem of, how do I keep my memory from getting fragmented? There's this piece and then there's this part, but we gave that back because the person called free, and then there's this piece. So how do we prevent this situation from happening? Well, that's pretty advanced topic. So we're not going to try to do that tonight. So it's sufficient for you to just always return memory and don't worry about running out, because when you run out, all you have to do is just crash.
Okay.
Technically, malloc doesn't crash. Malloc returns null. So if there's no more memory left, you have to return null.
Okay.
Okay. So
not quite a crash, right?
That's not a crash at all, but it usually ends up being a crash because who checks the return types? Well, it's common practice not to. So crashing is probably safer. like I said, you're lucky if it crashes. So you could build your version of it to be non-conformant and always crash whenever you run out of memory. So free really has to do a lot of work normally, but for your implementation, free is going to be really easy. All free is going to have to do is just say, well, we're done with this, but we're not going to give it back. So you're just always going to keep allocating forward. Make sense?
Okay. I think so.
All right. Well, so in order to do this, we need a chunk of memory, like we said. So we're going to call that chunk. All right. Actually, each of those was a chunk, so we can just refer to this as the heap. But let's not overload the word heap too much. So let's say that this is our pool. So you're going to allocate memory out of the pool. This is commonly called a pool, actually. But so your pool starts somewhere, and then you have to kind of keep an eye on how far you've allocated, and you're going to have to keep updating, like, okay, right now we're here, then we're here, then we're here, then we're here, because it was a big allocation, and so on and so forth. So we just have to keep updating where like kind of the next allocation is going to come from, right?
Mm-hmm.
Okay. And when free comes back, we don't really have to worry about, now a normal memory allocator would try to reuse the memory, but we're not going to reuse it. We're going to say it's burned. So once the memory is freed, it's just burned forever.
So what we're essentially doing here then is we're rebuilding malloc? That's kind of what it sounds like. Okay, all right.
Yeah, we're trying to build a simple version of malloc.
Okay.
To get kind of a sense of what malloc does, how memory allocation works, and it's not some magical like second language that comes in. Like malloc is usually implemented in C.
Okay.
All right, so we're doing our design. So we know that we need to know like where the head is. So like what I guess we could refer to this as the head. So this is kind of like where the next allocation is going to come from. So this is where it is. This is where it is. This is sort of like the whole chunk. So we can refer to that as the whole pool. And we need to know where it ends, right? So this is the end. And after that, we need to return null after that because bad things, or we could crash or whatever. Okay, so malloc, we cut a piece and we give it back, right? Free, we're just going to burn it. So,
Okay.
You good to implement?
I think so.
Or do you have any other design questions before we get in there?
So I guess this is probably a very silly question, but like I understand why for a simple version of it that we're just going to pretend that free sort of, burns it, right? But like why, let's say in your example, so you have this pool, and let's say that for the sake of argument, it's like subdivided into like 5 evenly spaced or even not evenly spaced things. And 4 of them, the first 4 are like, you can make them however big. And the first 4 are occupied or they're being used. And then we free the third one. And there's something that I'd like to store that takes up 2 of the chunks.
Mm-hmm.
Why does it have to be contiguous? Like, why wouldn't we just say,
that's the guarantee
sure,
from malloc.
Why?
By definition. That's the definition of the malloc interface, is that you get back a contiguous chunk of memory.
Sure, but why? Why is that the definition? Like, wouldn't
How do
you be able
I
to
know?
use more memory if you could say take that thing I want to store and store it across those 2 chunks of memory?
So like you want to
conversations
hand
about,
back like this one and this one?
Mm-hmm.
Well, how do I know how does malloc know how you're going to use the memory?
But why does it need to be contiguous at all?
Because let's say that I set myself a character array and I wanted it to be, it's a buffer. And I want to get like from your allocation, I want to say I want to malloc 1024. Or let's write correctly. So let's say that we want to get a K. What would happen if the middle of this thing was not contiguous? Later on, at some point, I'm going to be doing like buff of 511, and that's going to be a byte that I assign something to when I str copied into it. And then when I get buff 512, how would this work? I would have to add a whole...
The way that we've talked about things being stored in memory, especially with we don't need things to be contiguous. If they're like padded out, we don't have to worry about things being split over necessarily.
Wait. Think about the programmer who's going to use this interface. Like they would need to know how to deal with things being split.
I guess I don't understand why.
Because like, this what I just wrote doesn't work. From buffer 511 is basically taking buff and it's doing a pointer offset because this thing's actually a pointer. And it's adding the size of char times 511. It's actually doing a pointer offset to get that memory location. So to get this memory location, it would be buff, whatever the address is, plus 512. Except it's not, because now we're not guaranteed it to be...
You can't have like relative addresses?
Oh, well, that would be a whole other language you'd have to build to like trace every future access. I mean, how would you do that in C? I mean, you would have to trace whenever the user was accessing the memory you gave out, and you would have to patch it on the fly to say, oh, that's not actually here, it's over here.
But especially with the use of something like pointers, I feel like that kind of idea of relative addresses is almost already built in.
Okay, if you feel strongly about this, let's just talk about it at the discussion time, because I can tell you that that's almost an entirely separate language you're creating to handle that. So we'll put a pin, why contiguous, and we'll discuss that at the break, because you're going to need basically the full clock to implement malloc with the contiguous sense.
Okay, I was just curious like why it had to be contiguous, that's all.
Okay, it's at the moment it's by definition the way the language works. So that's for the moment all you need to know. But like we can get into why they chose to do it that way at the break. Well, at the discussion. All right. So that question aside, any other questions before you implement?
I don't think so.
Okay. Let's go do it then. And of course, it wants to get rid of your window. That's nice.
Oh, stream.
Oh man, what's it doing? Okay, something bad happened to OBS.
Oh no, OBS.
OBS. Why? Why do you do these things, OBS? All right. You can already start typing, and I'll just fix your window whenever I can figure that out.
I mean, I'm a little bit, I understand conceptually what we want to do, but given that the way that we've learned to take chunks of memory and set them aside is malloc, obviously we don't want to use malloc because we're trying to build it. So
yep.
That's the way that we've learned to like engage with memory really is through malloc. And so
yeah, so we got to build it. We got to know how it works, right?
Right, but we haven't really learned any other way to access memory, right?
Well, I mean, that's literally what you're building right now, right? I mean, we're basically using arrays to build our version of malloc. Okay, Skype is really being a douche. Okay, I re-added the window, so I'll fix the title bar in a moment. Okay, so you know what start with writing the interface. Like what does it have to, for what write your malloc function. Let's call it emalloc for Enceladus malloc.
Yeah, I was thinking about that, and I was trying to think of what it would return, right? Because technically it would make sense for it to return a pointer to the start of the chunk of memory that we want it to set aside, right?
Yes.
So, but that's not necessarily a void pointer. It's just a pointer. It's a pointer to some memory address. So I wasn't sure what that had right then.
This part is actually super easy because you don't get to choose the interface because we're going to build exactly the interface that malloc uses from the library. So this isn't like a design decision. We're going to make something that's compatible with the existing malloc implementation. So when we're done, we should be able to use, and so I just copied you could use it. All right, and you can build free as well. Now free is going to be kind of a no-op. It's not really going to do much. But we have to provide the if we have an allocator, we have to have a deallocator. Mm-hmm. Okay, so. Malloc sounds like a Harry Potter villain. Yeah, totally. Whereas if you make a malloc that uses every single byte of memory from start to finish all the time, you get okay, Surfing, we're going to get into that in the discussion. Smoke clinics, allocate contiguous block at different address. Yeah, okay, that's true too.
Hi, Foffy.
And hi, Foffy. Sorry, I missed that.
And Josh Perry, you got
next project, some OBS. Nice. Yes, OBS is just, I don't know why it just did that. All right, so anyway. Let's build. So emalloc, you know what the interface is.
Okay. So it's T.
I'll even
I guess
come down here and call your function for you. I want 10 bytes.
So the way that I'm thinking of it kind of even in pseudocode, right, is that we have to start at the very beginning, like the most easy is all of our pool of memory is free, so we can start at the beginning. But how do we define that pool of memory?
Yeah, we got to start with a pool, right? So let's start with a pool that's 2K.
But how do we do that without using malloc?
Yeah, I mean, how do you refer to a byte of memory? What data type do you have that's 1 byte?
Characters?
Yeah.
Right?
All right, so let's use unsigned char because we don't really want to and this is common. Unsigned char is usually used to refer to a byte because it adds no semantics. It's just basically like kind of the raw byte. Okay, so we have an unsigned char.
And instead of pool, we're going to call it
Wait. We need an unsigned char. That's a signed char.
Oh, I don't remember how to do unsigned char.
It's not a remember thing. It's
okay.
it's you just do it. Okay, Except 2K in the computer sense is 2048. So it's powers of 2, right? You can learn the bad habits later from...
So, I'm sorry, what do you... Okay.
That's 2K to a computer.
Okay.
Okay. Now, allocating this thing inside emalloc puts it on the stack. It's a local variable to emalloc, which is going to be a problem because when we return it, it's going to destroy the stack for the function when it unwinds the stack. So we can't put it there, at least not using only the things that I've shown you so far.
Okay.
Where can we put it that it'll live beyond the life of the function?
Well, so this is where we kind of get into the trouble of we haven't really talked about how to build functions that can be called from other programs before. Because if it's in main, then it can only be called when this program's run. But if we need it to be something that will be called whenever malloc is run, I'm not sure. It feels like it should be like outside of all of that, like just here.
Yep. It should be in global space.
Okay.
Okay, so chunk. This is our pool. You might want to use the normal terms because they're going to show up in the documentation.
Okay.
You can use chunk if you want, but you might be confused later when you actually start reading about memory allocators.
Okay, so then...
Hey, Akshay, how's it going? Yeah, kibibytes. All right, we'll get into that at the discussion, Strophium.
All right, so let's think about this.
She's got to learn the term pool, don't you think? Yeah, I know. Will it help you if we make it chunk?
No, it's just like when I'm writing things, at least just being silly and stuff like that, I feel like just adds kind of like a humor element. But
I'm just worried that later on this is going to be hard. But all right, let's go with chunk.
So,
Okay, so we have a chunk. We have a chunk of memory, which is what we're going to divvy out. So that's our whole pool. And what we need to do is we need to kind of keep track of what with it.
So we need to keep track of what's been used.
Yes.
What's already kind of been allocated, right?
Yeah.
So where we are exactly. So I think we need one more global variable, to be honest, which is like our place.
Sure.
And
now, by the way, to do a memory allocator, you're going to need to use some memory to do your own bookkeeping, right? So like memory allocators aren't free, right? They need a little bit of memory to do management of memory.
So I think it would make sense to just kind of like have this is basically our index, right? And so I think if we just kind of have like to start out with, right?
Okay.
And so that is a variable that we can then update whenever, malloc is called. So we do like index plus size.
Okay.
Index equals index plus size, right?
Cool.
So that'll change sort of what the index is.
Yep.
Okay. All right. So.
Except, do you want this to be able to be negative?
No. So I guess we can just do like an unsigned.
Yep. Yeah, it shouldn't be a sign type.
Uint.
Well, you can use the classic type. So unsigned int is fine. Yep. Okay, so we don't allow it to go negative. It's this thing's positive.
Yeah, and that makes sense. Okay, so JavaScript is for fun. Oh,
yeah.
Josh Perry.
I like the C for seriousness is like I sort of lolled a little bit.
Anyone who thinks JavaScript is fun though. No, I mean I'm not into like, pooping on various like coding languages, but JavaScript, oof. I'm not sure if I would describe that as for fun.
Oh, chat, by the way, how are her levels compared to mine? Are they like kind of like roughly even?
Oh, we forgot to ask.
Yeah, we forgot to ask. Like I had to quickly set them up. So if she's a little quiet, let me know. Or if I'm quiet or whatever. She's a little low. Okay, I'll turn you up a little bit. All right, so when she says something, you can tell us more.
Test. Can you hear me better now?
Sounds
Thank you,
pretty good.
Franz.
She's a little bit low. All right.
Still low? Okay, better.
Yep.
Better. All right,
Okay.
good. Okay. All right, so let's think about this. So the memory, the piece of memory, so the like piece, we're gonna need to say, hold on, let me think about this, okay? So we did unsigned character, right? So this is gonna be piece of memory, right? And this is going to be let me think about this. Hold on. So I don't even know if I can index like this, but like index, right? The start to index plus size.
Wait a minute. Hold on one second. Brenner, let's not crap on people with programming languages. Let's just let it go. there's good people in JavaScript. There's bad people in JavaScript.
Yeah, I mean, I actually know a few JavaScript programmers who are beautiful, wonderful people.
They're not all bad.
I just am very bad at JavaScript, and so so they can do things that I cannot.
By the way, I dislike JavaScript too, but I don't dislike all JavaScript people. I mean, it's
yeah, Strophium kind of has exactly my approach, which is this. It's something that I'm less interested in.
Yeah.
Compared to other programming languages.
Honestly, after doing a bit of front end work, they earn their pay.
Seriously, I have so much respect for like UI UX designers, front end developers. Like,
yeah.
No, I'll stay in my happy back end land.
All right.
For sure.
So explain what's going on here with your slice that doesn't exist in C.
So essentially what I'm thinking is it's kind of like when you're integrating from like x to x plus I, right? Except from here, we need to allocate a chunk of memory. So we're slicing from the index, which is our changing start point, right? From start to start plus whatever the size is.
Yes.
And we know that the index of our array, thankfully, because we picked characters, is actually like, pardon me, 0 to 10 would be 10 bytes
because we're guaranteed contiguous memory, but we'll get back to that later.
But the indices that I need are going to be essentially the end of the chunk minus the start of the chunk is going to be the size. Our indices work that way, thankfully, like we said, because we set it that way. So we need to index, we need to take a piece of, oh wait, this doesn't make sense. Hold on. I got you. I figured this out. That doesn't make sense because we actually need this to be the
that
size.
Big. Yeah.
Yes. And then it's going to equal
from there to there.
Yeah. And so you said I can't do that, fine, but that's sort of the approach that I'm thinking.
Yep. I mean, that pseudocode wise, that kind of makes sense. Okay, so how do we actually do that, right? I mean, that's pretty much what we want to do is like return the memory from there to there. So,
well, so I've got a question actually. I think this might work because given what we were talking about arrays with pointers, so okay, let me talk out loud and see if I can figure that out. So,
well, first of all, what's the return type you need to actually return?
The return type that I need to actually return? What do you mean?
What is
void?
Yeah,
it's void.
It's not just a void; it's a void.
Void pointer.
Yes. So let's declare one of those because that's what we're going to have to give back.
Okay. So, I don't know what to call it.
I mean, Brenner, you're definitely entitled to your opinion. We could also get into a bit of language fun. I'll pin that as a topic. JavaScript language. Okay, keep going. Sorry.
So, okay.
I do what Strophium says, by the way. I always name my return result. But yeah, you're calling it thing. Thing's good. I like thing. So we need to basically fill out thing.
Right. And so here's what I'm thinking is that, okay, I have to think out loud when I code. So it's
No,
really
it's
funny
fine.
actually when I'm programming at home because I'll just be like talking to myself.
Totally fine.
But so, all right, so the piece of memory that we've assigned, right? So this is an array. And actually, no, I don't want this. I don't want this. This is a bad idea. So I'm actually going to do that for now because I don't think that's actually a good idea. Because I think what we need to do is we already have the size.
Mm-hmm.
And while this would work if we had already declared the size, we need the pointer to it.
Mm-hmm.
And so what we actually need is like a little, well, an array. Right. Okay. So, I'm like there. Hold on. So this, yes. Actually, yes. And the thing is that a void pointer though. But I want to return just a real pointer, not a void pointer.
Except
so
the interface is void pointer.
Oh no. Okay,
you don't get to change malloc. It's been around longer than you were born.
Old things aren't necessarily good.
Nope, but we are building something that's binary compatible with the old interface, so we have to do it that way.
So all right. So in this case then, we're going to cast it. I don't even know if that's going to work, but that's like the only thing I feel like I know how to do right now. So this piece of memory, right? We've decided we're going to, I feel like I know that I need to declare it, but when I declare it like this, I feel like that takes memory. Or does it take memory? It does.
You don't get to declare it.
I don't want to declare it. I want to just say that it is equal to something. So can I do that when I declare it?
So if you declare it there, where is that memory?
I don't want to do that.
Yeah, you can't because it'll be in the stack frame of emalloc. So by the time you return, it's gone.
But is there a way to like, so can I say that this is like, this is equal to, this is the problem, right? Is I want to do that again, like index plus size thing, right? And I know that doesn't work.
Yep.
So
in the existing malloc, how do you know where the end of the memory chunk is? How does it tell you?
What do you mean? How does it tell me? It doesn't really tell me. It just gives me the pointer to the start.
Yep.
But we have to know that within malloc. No, but within malloc, it has to know that that memory is available.
That's true. So that's your own bookkeeping, but that's not related to what you have to return. You don't return a slice. You're returning just the start of it.
Right. Okay. So that's true. All right. So hold on. So really what we need to do here is, all right, so this was wrong too. Hold on. So that's our return, and this is going to be, and so what we actually want to do is, all we need to do actually is check, since we're burning the memory and the memory is going to be contiguous, all we need to do is check that the memory address at index plus size is free. So there's like I don't know if C has like an assert, but there needs to be something like an assert. It does,
but you don't get to use it. That's a debug thing. So let's skip assert for the moment. Your math is absolutely right. So how do we know where the end of chunk is? Like how big is chunk?
2048 bytes.
Yes. And we have an operator that'll tell us how big chunk is in the event that you change that number.
Size of.
Right. So if we wanted to build another global, I don't mind that we're going to burn a few variables to make this problem easy. I want to make this problem as easy as possible. We can always build a more efficient version later. So how can we assign the size of chunk? Like, so we can say like total memory or something. Like, can we make like another size t, which is the total amount of bytes available?
Because that's actually, so that would be, in my mind at least, because we have a couple of assumptions, right? Our assumptions being, and at least just the physicist in me, bear with me. So we're assuming that memory is going to be allocated
Yep.
contiguously, and we're assuming that freed memory cannot be retrieved.
That's just for our implementation.
this.
Yeah. The
So
first
these are
one
the
is actually a
assumptions
rule
our
of
program.
malloc. The second one is an assumption. That's a simplifying assumption.
And that's fine. These are the assumptions. And so
Yep.
because of these assumptions, we don't need a third variable that is how much memory is left, because our index is our proxy for that.
Okay.
Because that would just be 2048 minus index, and that's how much memory is left.
Let's do it for cleanliness, because, rather than putting 2048s all through your code, we could just have a single 2048, and then we could say the size of chunk is how big it is, right? So
I'm not sure I follow you. I'm sorry.
This is kind of where I'm leading. So let's say that we, and actually you're using unsigned ints, so I'll use unsigned ints. Well, actually this is total memory. And this is going to be the size of chunk. Now, this isn't a big deal for C, because this is this is known at compile time, right?
Mm-hmm.
So the compiler can put that in. Like we can run this thing and we should be okay, right?
So.
Okay, built in.
Oh, is that already something? So I'll just call this I.
Wait. Oh, I mean, normally unsigned.
So it's a built-in function. So
normally
that's fine.
unsigned is no. Don't use I, because it's like everywhere. Like, so if you put that, we'll use index, but.
No, it's saying that there's a built-in function called index.
Oh, okay.
And it doesn't want us to use. That's why I said let's
use let's not use I, because I gets used in almost every function as a counter. So you'd have a global one and then a local one. That's bad voodoo. So we don't want to override the same thing. Let's call it like chunk index. Just so that we don't trip over.
Okay.
Okay. So we're back to compiling clean. Okay. So this line works, line 8, because the size of chunk is known at compile time. Right, it's 2048. Now, the nice thing about using this is that I don't have to put another 2048. I mean, I could just put this in here as like, this is also 2048. And I could just have 2048s littered all through my code. But the problem is that that's not really good programming, because then I'd have to replace all of those whenever I want to allocate more memory.
Okay.
Okay, so we know where the end is. We know where we currently are is chunk index. So, all right, back to your emalloc. What do we got to do?
So we need to check that. So the thing is that you're using this like size T type that like we haven't really used that, apart from just like it being in some of the documentation we've looked at. And so actually hold on, I've got an idea. I don't know if this is going to work. I'm going to mess around a little bit. Hold on. So I think it would be interesting to say that we have that is see, this is why like I kind of like the idea of having, because we could
you've
just
already
kind
declared size.
Where?
It's in the email.
Oh yeah, that's in the and I want I size to be equal to like cast onto the size.
Oh yeah, I mean you could do that, but I could tell you that size T is just an integer. It's an unsized integer.
Okay, so that's the thing, is I haven't really used that just data type before. So
it's a standards data type. It's not used in general programming, except it's defined exactly as the type that size of returns. Mm-hmm. So that's why it's used in standards instead of using int.
But it's a number like I could add.
Yeah, because int is one of those like we don't exactly know what size int is depending on the platform. Like so, size T is kind of like they don't need to be exactly the same size. Right. Okay. Size T has to be exactly the size that size of returns. Int doesn't. So it could be or it could not be. But that's the reason why we're using size. They're basically both numbers. They're both integers. But
so I have a question. So if I want to print something that is at a certain memory address.
Mm-hmm.
If there's nothing there, will it return null?
If there's nothing at the memory address?
Mm-hmm.
C doesn't make any definition about what's at a memory address you didn't initialize.
What do you mean?
So if you didn't explicitly write something to a memory address, it's undefined what it's going to return. It could return null, it could return not null, it could return anything. We don't know what it'll return.
Well, let's use the unsigned character array that we have. If there is nothing at array index 5 and I say print chonk 5.
Yep.
What will it print?
What do you mean by nothing? Was something written to there before or not?
That's no. So I'm asking this because I need this as a check. So let's say that nothing was written there before.
Then you have no idea what's there. The language gives you no guarantee about what was in that memory. It's undefined what was in that memory if you haven't written anything to it.
So I feel like we need to fill.
Yeah. That's the first thing we probably want to do is define that. So I don't want to define it in malloc because then it's just going to be overwriting things. But I think we want to do that. So chonk. Yeah, but keep in mind, we don't get to change the interface to malloc. And malloc does not require that you made an initialization call in advance.
Okay.
Right. I could just start using malloc in the middle of my program. I could go malloc 5 and that just works.
Right.
I never had to say I never needed to say init malloc before I use it. So that would be changing the interface if you add another function to initialize it.
I'm not adding a function.
Okay, so the only place that you could possibly initialize it is in emalloc. It has to be in emalloc.
We can say unsigned int chonk index equals 0, so why can't I say this equals however many zeros or
2048? Yeah, I mean, yes, you could, except in practice that would be messy, right?
But so that would give us that would fill this with some predefined thing that
you're correct. So if you wrote out 2048 zeros, it would be predefined. But let's assume that you don't want to write out 2048 zeros. So
I would figure that it would have some
you can't. Okay. I mean, so the one operation you have to be able to fill an entire chunk of memory is memset. So I'm not sure if you remember it or not, but we briefly touched memset.
Okay.
So let me just pull it out of my local man pages. So memset is very useful for this kind of thing. So basically we have a function that looks like this. Don't worry about the return type in this case. So we're just worried about, this basically says pass along a void pointer, tell me what you want to set at each location, and tell me how many there are. You'll notice, by the way, it's using size t because it's a memory offset. Whenever you're talking about memory offsets, it's always a size t, even though that's really kind of an int. So what we can do is, how do we initialize this memory? So C would be, you want it to be null, so that would be 0. So, and then S, what's the memory we want to clear?
Well, I don't think this is a good idea because the whole point is that we need to have a check to make sure that we haven't allocated this memory already, right? I feel like that's an important part of this. And if we just kind of overwrite this memory every time we're using it, then, well, maybe not. Okay, hold on. I think I see where you're going with this. So
chat's getting really fired up about this. Josh Perry, it actually, on a Linux system, it will clear it mainly because of security reasons, because they don't know what memory was there before. So it'll almost definitely have been cleared, but it won't be on the other systems that we're going to be using. So let's not get into bad habits. They're talking about putting a poison pill in those addresses, which is another good technique, but I don't want to, it's a little bit more advanced. Let's for now, let's just zero the memory. So we'll assume that our allocator takes the hit and zeros the memory.
So
Jay, don't go trying to give her an answer.
Okay.
She's got to work it out.
I'm not even reading chat, so you're fine. What is C again? I'm sorry.
Let's not initialize the chunk. Let's just one time initialize the entire thing to be 0. Because we know how much memory we're going to have for the entire execution of this program, right?
But I actually, I thought about that, right? And I thought about, because we said, let's do that, let's set everything to be zeros. But here's the thing, is that we have a built-in way to tell if we've allocated this memory already, which is this global thing, chonk index. If the chonk index is above, like, we have that protection already in place. And so we don't need to fill it with anything because we can just overwrite it.
You want to clear the chunk that we're going to return every single time?
No, but I think, so no, actually, I don't even think we need memset.
I mean, we could just return whatever happens to be there and leave it up to the OS. But let's for good practice, let's just clear the memory. Let's say that our allocator always returns null cleared memory.
Right. I don't think so. I feel like you're almost contradicting yourself. So you say that, like, outside of the function definition for emalloc, we can't initialize another function. So
nope, we have to do it in emalloc.
Has to be in emalloc. But then we necessarily, by definition, can only clear the chunk that we're setting aside. If we re-clear chunk every time, then we're overwriting potentially.
So what if we just do it once?
Memory that we gave to somebody. What do you mean if we do it once?
Yeah, let's just do it once in the beginning.
But there's no initialization or whatever. So it means the first time somebody calls malloc, it okay.
Let's add another variable, which is chunk initialized. And we're going to start it off as it's not initialized. So it's equal to 0. And
I just feel like why can't we return, just clear the thing that...
We could, except that now we're getting into the complexity of always calling a memset. So first of all, it's faster, because I guess we shouldn't worry too much about speed, but it's faster if you just do one memory blit. Like if you just tell the thing, like just clear all this memory. Because right now you're dealing with like 2048, but on a real system, like malloc is going to have gigabytes. So if you're clearing like all the time, like, yeah, you could do that, but then you don't know, like your allocator won't, I mean, let's just go with like, we clean it up front, so.
Okay.
We can use chunk initialize to figure out if we've initialized memory or not. So what do we start with?
And then what was C again? Int C, it says?
C is what each location is going to have. So in this case, yeah, 0. Yep, no, you had it. That's null.
And then...
Except we don't have to hard code the number. Where do we have the number? Yeah, we could do that. Or, I mean, you could also just use... The problem you have is that you don't know if this is a variable, like total memory. So we don't know if total memory was ever overwritten accidentally. So let's just be a little bit more defensive. We'll just be careful. So here we're just saying...
Now, what is even the point then of having line 8 if we're going to call size of chonk in our code?
We're going to use that for...
Seems kind of
we're going to use that for bookkeeping. Okay, well, hey, I'll delete it then.
No. I just, do you see what I mean? Like, if we've defined a variable
you sold me.
to be a certain thing, if we're not going to use that
it's
variable,
gone. It's sloppy.
Okay, all right. I just
okay,
that's
so
my intuition.
This right now, this memset is going to get called every time we allocate. Is that what we want?
Right. I'm not there yet. I'm sorry.
Okay.
I wanted to get the because I've never used, or at least I don't remember using memset, so I wanted to get the syntax down, but you were absolutely right. We are going to put this in an if. Oh Lord, it's been a while. So
Erzig, you're right, by the way. I mean, that's so we're going to see if she watches her bookkeeping or not. But your intuition's in the right place. Josh Perry, no, the interface to malloc does not guarantee a 0 init. Malloc on Linux guarantees a 0 init, but that's not malloc in the standard. It does not require a 0 init. We're going to do cleanliness now.
And so actually, I can't remember. I'm sorry. I was focused on this, so I don't remember if you responded to this. But this is actually a really good question. Is Erzrig, and I was actually going to ask you this, so thank you for bringing it up, chat. Or Erzrig. I'm trying to make sure I say that right. So Well, I guess so. So actually, to answer that question, I don't think it's going to be an issue if we ever want to write 0 to the array, because we're just handing the memory location. And if they want to overwrite it with zeros or whatever they want, that's totally fine.
Mm-hmm.
But we're only going to be running the 0 initialization once.
Mm-hmm.
And then after that, like, this can get filled with whatever. And I think you're probably thinking of what I believe malloc can already handle, which is that freed memory can be reassigned. And in our particular sort of like simplified example, it can't be.
Mm-hmm.
So
actually, there's
really
also something else which he's worried about, the bookkeeping. But we're gonna, I think, if I'm getting his, well, yeah, I shouldn't say his. If I'm getting Erzig's right, meaning right. So we're gonna worry about bookkeeping, because if we handle our bookkeeping correctly, we're never going to be looking at the memory we're about to assign. We're just going to know exactly how much we need to assign.
Right, and we only pass the addresses. We don't even need to know what's going into that, right? Okay, but
so we're going to be careful about that. So the intuition is definitely in the right place. So what's wrong with this as you just wrote it?
Oh Lord, probably something with my syntax. I don't really remember.
No, syntax is all fine. It will. This says if chonk initialized is 0, then mem set it all to 0. How often will that run?
Once.
Every time.
No, because we're going to, the first time we run this, set chonk initialized to be 1.
Did we do that?
Not yet.
Okay. that's
no,
what
so that would be something kind of like at the end, is that we'll say,
no. Why don't we just do that once?
Chonk initialized.
You could put it there, but let's put that in the brace so that it's related to when chonk initialized was 0.
Oh, I see what you're saying. Okay.
Yeah, this is kind of just good practice. The way you just wrote it would work too, but usually you want to put that like wherever you're kind of testing it, so that like immediately you step on that condition.
I see what you're saying.
This is, by the way, this is called a one-shot in classic world. So we're using chonk initialized as a one-shot to basically say, have we run this or not? And the first time you run it, clean it up, and we can also sneak any initialization. So this is how we actually add an initialization function within our function. So this is kind of like to your earlier point. Like malloc doesn't have an explicit initializer, but the first time you call it, it can do some bookkeeping.
Mm-hmm. Okay, I see what you're saying. All right, so we can now move forward, clearing or knowing that our memory is cleared. And so we can...
By the way, Brenner, thank you for the follow. I appreciate it.
Oh. And so let me think this through. So we need to... So... I know we need to return that, but I'm actually thinking through. So we need, hold on. So I'm just this might be pseudocode, but just like don't look at it teacher for a second. Okay. So
I'm not looking. I'm looking.
Starting place, right? So chonk index. It's going to be our starting place. And really, okay, so only the first time could we use the trick. So what we need to do is we need to pass off the address to this.
Mm-hmm. Yep.
And so that's going to really be what we return, but it needs to be a void pointer. Mm-hmm. So I feel like I'm not using a Mac. Okay. Thing is going to equal.
Nice cast.
That is going to be the pointer that we pass off, that we return. We're going to eventually return thing.
Mm-hmm. But wait, I'm not looking. Right. Sorry.
Okay. Yeah, you're not looking.
I'm not looking. I'm looking at chat.
None of that. You talk to people. All right. So.
Strophium, no, but I should add that. That's a good feature.
And because size underscore t is an int, we can add it to things. So chonk index is going to equal. I don't know if I can plus equals size. There might be some 0 weirdness here with indexing, but I'd like to at least see if this would work. Let me think about this. So if we start out with 0 being the start and somebody asks for 10 bytes of something, we'll give them back 0 the pointer of 0, and they know that they can fill 0 to 10 with whatever they want. Chunk index is going to be, the size is 10, so 0 to 10. So this needs to be size plus 1.
Really?
I think. So no, because the 0.
What if they ask for 2 bytes?
So if they ask for 2 bytes, they get 0 and 1. So that yeah. No, you're absolutely right. It doesn't need to be the plus 1.
Yep.
Okay. Yeah, we're good. Okay. And then so let me just go back through here. So we have our initialization. The first thing we do is we clear memory, and then we set it to be, okay, fine, it's initialized. We're not going to clear things anymore. Then we pass the address to the start of the chunk that they want, and cast as void pointer because whatever reasons.
Mm-hmm.
And then
that's the interface. We don't get to choose the interface.
reasons. And then
this is we're building our version of a traditional interface, so we don't get to change.
Okay, I think you can look at this now.
I can look at it. Okay.
I think it's.
I'm looking.
I'm
looking.
It works. Okay, I think it works.
Okay, thing. Yeah, you're doing a little void pointer out of the address of chunk index. Looking pretty nice. And then you move chunk index forward, which is pretty cool. So next time chunk index will be at the end of that. And we return the thing. Let's find out. It looks good.
Okay.
Now, I'm just syntactically, we always keep our return, little minor nit. And we usually put declarations up at the top, but
I wasn't sure if it would go before or after that, like one-shot initialization. So I remember us talking about how declarations go at the top, but then I wasn't sure.
Classic compilers, and actually I was just doing this on stream the other day when I was doing the Nintendo game, like they actually will reject anytime you have a declaration that's after code. It'll just reject it. Yeah, like the NES, the CC65 will just reject it. So like here we get the option because it's really GCC underneath, but I can tell you that like a classic compiler will kill you if it's not here.
Gotcha. Okay, no, that's good to know because I wasn't sure.
It literally just has to be up front. Now in C++, we usually try to put things a lot closer to wherever they're used. This is a pattern which is called resource acquisition is initialization. So when we create the resource, we want it initialized right at that moment. And that's to disallow the ability to have code in between. Like we never want to allow code to touch it when it's uninitialized. So initializing it on the same line. Now, the way I've been sort of showing you is we're just not using the fast. We're doing this, which is somewhere in between the two. So just stylistically, that's fine. I
like the other thing you wrote.
We're going to do that more with C++, but that's definitely the idiom in C++. But I'm okay with it either way for this. I mean, so if you want to.
Okay.
Now, Martin Fowler would say, well, you don't even need this anyway because you can just anyway. So we'll get to that later. But
so to Erzrig's point, we're not rebuilding malloc exactly. So
yes,
just as an FYI, like this is sort of like baby malloc.
No, and Erzrig, no wait, hold on. Erzrig. Okay, let's try to say it right. Okay, Erzrig. You're absolutely right. Malloc does not guarantee 0. That was just that's just because of this. So no, your memory is absolutely correct. But memory.
Yep. Okay. Your memory is not leaking. Okay, all right.
I got to get a rim shot. That's just.
So, all right.
I rewatched the stream, by the way, and Strophium had a great one the other day when I was like going like, I'm like, yeah, let's get our intuition, and it was like Strophium pointed. I didn't even realize I punned, and I loved it.
He's very good with the puns, so like
it was good.
Okay, so
Jay, that's an advanced topic. Is the answer to that? So right now we're building a memory fragmenter version of malloc. Malloc doesn't say anything about it being, as I pointed out to Jess early on. We're not trying to build a good malloc. We're trying to build a correct malloc for right now. So we're not going for the most optimal yet. We're going to start with getting it right.
Sorry, copy paste.
Yeah, and Strophium's right. Yeah, when you run out of memory, go get more RAM. That's. He's talking about a hard drive, so virtual, swapping. But anyway, we're not worried about that. That's implementation details.
Okay.
Except it's always an implementation detail because it's programming. So.
All right. So.
Okay.
Oh, so well, that's
no big deal there. Yep, we add string.h. By the way, I'm going to add your assumption. Well, I'm going to add the stipulation, I guess. Stipulation. Our version zeros memory. Zeros, there any? Yeah, I think so.
There's an E.
Zeros memory for you. So this is off standard. But we're just doing that. We'll add a poison pill later. That's kind of why we're doing it.
Okay. I guess, like, if I were writing this in a language that I knew a lot more in depth, especially since right now it wouldn't return anything, I would probably have more sort of like debugging checks and things in there to make sure that it's doing what I'm telling it to do.
We'll do that. Let's start with this. Okay, so for right now, we have something that compiles, right?
Sure.
Okay, so
it doesn't break.
It doesn't break, or at least
not that we know.
Yeah, we don't know. Okay, so what's the first thing we want to do with it before we start adding some debugging? Why don't we try using it according to the specification?
Okay.
So we have an emalloc of 10 here.
Mm-hmm.
All right, let's look. Let's use it. Let's pretend that you actually use this instead of malloc. Actually, there's no pretending. We are doing that. So let's use it the way we want to.
So here you just kind of like.
So let's not do 10. I just wrote that as a quick placeholder. Let's dynamically allocate. Let's start with just an integer. Let's dynamically allocate an integer.
Okay.
Yeah. Yeah.
No. So each one is we have 2048 because.
Wait, you don't know the implement. You as the user now don't know the implementation details of the allocator. Okay. So this 64 you want 64 bytes?
No, God. See, that's what I was trying to do in my head. All right. There we go.
You want 8 bytes? Okay. Or if you didn't want to remember it because you want to write it to be more portable, you could have the compiler figure out what the size is by doing what?
Size of.
Yeah, so let's do that.
Okay.
Oh, you're going to make it unsigned? Okay, I was just making a regular int.
Okay. Int.
Okay, and let's store that. Let's make a new int pointer that's going to take that value.
So I need to do that before this.
Mm-hmm.
Okay, so we'll just call it
other thing.
Other thing. I like that, other thing. Okay.
What type is other thing?
So nope. I'm working on it.
Nope.
We want this I want this to be a real pointer because I want to cast it. I don't know how to cast. How do you make something a real pointer from a void pointer?
You cast it to a real pointer type.
How do you do that?
Well, first of all, what's the type of other thing? You still didn't put the
real pointer. Okay, sorry. Yes, I'm.
Okay, that needs
what were you saying?
That other thing needs a type. What type is it? What type do you want it to be?
A pointer.
Not just a pointer. What kind of pointer?
A real one.
Yeah, a real. What kind of real pointer?
We've talked about like.
What type is it going to be? I mean, what are we putting in there? How much memory did we allocate?
And that's okay. So I'm sorry. This is like we've done the file in all caps, right? And we've done void, but we've never really done like a pointer to something.
Yeah, that's it. That's how you do it.
Thing. And so
that's a concrete pointer. That's an int pointer.
But what? Okay, I have a question.
Now it's exactly the same size as a void pointer.
So I have a question about that.
It's exactly the same size as a char pointer. It's exactly the same size as a size t pointer, if I could have one.
Why do we have to say what it is then? Because it's just an address
semantics. They all have different semantics. Last week we were doing struct planets, and we did struct planet pointers, right? So our
Right,
concrete.
but it doesn't matter. It's just an address.
No,
in
it
memory.
matters. It's the.
Is it just so it knows what to interpret at
Yes,
that memory address?
yes.
Okay, all right, that makes more sense. All right,
Yes,
so
it's semantics.
This is, so then we need to cast it.
Oh, no, don't initialize it. Let's keep using your existing, we declare on one line.
Thing. Said that initialize as it was a fancy
No,
word.
that's C++. This is C.
But I like it. Okay.
Yeah, that's how we turn it into a real pointer. I like Strophium's comment too. It becomes real by proving itself brave, truthful, and unselfish. Nice. Don't tell her, Strophium. She doesn't need that detail right now, but he's right, by the way.
I don't know what that means, but okay.
No, Josh Perry, stop it. That's C++. We're not doing C++. Stream says C. We're doing C.
Good Lord, all right? I'm like not even there yet. So
casting gets even crazier in C++.
Slow down. Casting is really cool, and I really like the control that it gives me over exactly what's happening, because a lot of times
no there's casting in C++. There's just a lot more of it.
No, I think what I was getting at is that sometimes in Python, because things are like so much of the control is taken out of your hands a lot of times, especially when you're importing different libraries and whatnot, that you can run into a lot of problems that way. And so I kind of like how much control this gives me over being very explicit about things. Like I know exactly what is happening. That's nice.
I have to say one thing. Nice. This is not aimed at you. This is aimed at Nightshade Dude.
Okay.
Shaking my head.
Okay, good. All right,
I'm shaking my head, Nightshade Dude. Okay.
Okay, yes. Everybody, so I'm sorry, really quick.
You're right, by the way. It's very cool how the casting gives you the control, but it is really up to you as a C programmer to keep it straight.
I know like very little C, even less C#, and I'm very, very comfortable in Python and once upon a time, high school Jess knew MATLAB. So I've heard so much, mostly people dunking on, but I've heard so many things about Rust and they're all memes. So I have no idea what this language even is.
Don't feed the trolls. They're Rust or bust. They're getting a little crazy.
It's all the jokes about Rust, but like
Jay, I don't hate Rust. All I hear is
jokes about Rust. I don't actually know anything about the language itself, so now I need to look it up.
This program is a little rusty.
Opening Pandora's box. I'm opening Pandora's rusty box. Okay. So okay, right.
Nice one, Strophium. I like that joke.
We have a pointer to other thing is an int pointer, and we have cast it to whatever malloc gives us.
Okay, chat's cracking me up. Sorry. back to serious implementation.
But I want to. Then I can say. So, give me the thing. Okay, so actually, I don't know if this is going to work. Hold on. So other thing right now is a pointer. It is an address in memory. Mm-hmm. And I want it to give me, I want to be able to assign the thing.
That's for structs.
Oh, it's only, the pew operator is only for structs?
Pew only applies to struct pointers.
No! Oh, my world is crushed.
It's okay. It's okay. We allocated one int. We're getting back to our pointer basics that we sort of glossed over earlier. Yeah.
Boring. I don't get to use the cool arrow.
Yep. And reading that statement, it reads as
the I am dereferencing the pointer, the address in memory. So it's getting the thing at that address and it's saying it equals 12.
It's sticking 12 in there. All right. Let's try that. And we print it out because we want to see some output using the custom allocator. Well, I mean, we already did our custom allocation, but yep. Nice. Okay, why are we closing the parentheses?
Oh, Lord, why am I? That's a good question.
Okay.
Oh, oops. Yeah, this happens sometimes. Yeah, all right.
Wait, no, it's an integer. We want it to be D. You were right. The other thing
well,
was problematic.
Can I make it a long decimal though?
No, don't. It's an int.
No?
It's D. It's okay. But what's it actually thrown about?
Hold on. Format.
Well, first of all, the number is nowhere near 12, right?
No. I know. So hold on. Give me a second. So %d expects argument of type int, but argument 2 has type int. Oh, it's a pointer. Oh, duh. Hold on. So, oops, not that one. This one.
Mm-hmm. Hey, party time.
Hey.
Okay.
Now I have a question.
Okay, now you get a question. Of course, I want to see another allocation.
Memory address negative.
That's because of the semantics you added to it.
Semantics.
What are the semantics you added to this pointer? What kind of pointer is it?
Oh, should I've specified unsigned int?
Well, if you want to deal in ints, no, you should be talking about ints.
No, but the pointer should have been
it's an int. It's pointing to an int. The concrete type had better match the pointer type. Like you generally want them to be the same, except when you're doing this void pointer.
That's not the problem.
No, it's not that. It's trying to interpret a memory address as a signed decimal, as a signed int. And so that means that there's something in the high bit because, if we're dealing on if it's 32 bits for an int or 64 bits for an int, that means that the high bit has a 1 in it, which is going to cause it to show up as a negative number. High bit.
Sorry, I had to joke. But
Nice.
Is that the first? Because when we were talking about bits and how the sign is going to be that first.
Yep.
Okay, all right.
Yeah, it's that two's complement thing. But yeah, that high bit definitely tells you that it was negative, and so it's just saying, all right, you want to print this thing out as a signed decimal integer? Fine. I mean, that's negative then.
Gotcha. Okay.
Okay. Oh, and thank you, by the way, Dutch. That's a great name. Dutch caffeine. There's all sorts of wonderful things happening
coffee?
there. Is that just a coffee shop for the Dutch? Yeah.
Do the Dutch have other forms of caffeine? Clue us in to
Dutch,
your magic.
Yep. All right, we'll speak about the Netherlands later. Let's do another allocation.
I want to move there. Get me a job. Okay, yes.
And by the way, Jay, thank you also for the follow.
Not a coffee shop. Okay.
Not a coffee shop. Hey, Sunny, what's up?
Hi, Sunny. All right, so I am going to
Sang ho.
I'm gonna just copy this. Forward to notes. All right.
Hello, Dinosaurs. Hello, Guy. Hi, Sunny.
All right.
Sunny's my mod. Hello, Sunny mod.
Okie doke. So now we need to do free.
No. Let's not free. Let's do another allocation. Let's see if your program. I mean, that was just the first allocation. That was kind of the rigged case where it was like the first piece of memory. What about later on?
I see what you're saying. Okay, so
let's see another allocation.
Keep everything the same. I'm just going to pick a different.
Yeah.
A different integer. I'm going to clear the output.
Okay, so that's looking like it's operating correctly. Now let's beef it up a little bit. Let's allocate. So that's our first allocation was this emalloc.
Mm-hmm.
All right, so we have one called emalloc. Let's do another emalloc call. This time, let's allocate 5 characters.
So 5?
5 in a row. What do we call that?
An array?
Yes, that's it. Let's have an array.
Okay.
Let's have an array of 5 characters dynamically allocated by emalloc.
Okay, so
Jay goes, I bet $10 it's going to crash down. I think betting is against terms of service. I don't know with Twitch, but I wouldn't be taking that bet. Let's see what happens.
5 characters. Ha! My name.
Right. Wait, hold on. Leave that int.
No.
Leave that int. I want another allocation. I don't want this reusing thing. We already allocated that int. That's our first piece of memory. It's burned. It's gone. Let's do.
We don't need to.
No. Let's do 5 bytes after it. I want that first int to stay live on the Jess heap, and then we're gonna get to the next 5 bytes.
Well, copy and paste exists. All right.
Sonny, what kind of precedent are you setting for the channel? No betting in here. Other thing. Nice.
It's the little things that get you through.
Yep. Sorry,
the
I
rough
changed
days of programming.
Except we don't get to assign arrays like that, do we?
No, I'm not done.
Oh,
Hold on.
okay.
Hold on. Don't look.
Okay, I'm
It's not your turn. No looking yet.
totally
All right,
looking. Totally looking. Okay. Yeah, I like
Oops, not 10.
Erzrig's idea here. Let's put both printfs at the end to make sure that they're both live on the Jess heap. Well, the chunk, really. It's but...
I want to chunk. See, you've got to if it makes you laugh.
Yep.
It's a good.
I want to see it. Let's get it on the chunk.
Okay. This isn't ready for you to look at yet.
I'm trying not to look.
Yeah, don't look. So.
Look at this.
Because a pointer. Okay, so this I think is fine. There's something else that's bothering me here, which is that.
Wait a minute! You just allocated 5 pointers. No, you don't get to do the allocation. This is dynamic.
I didn't tell you to look
Okay,
yet.
sorry.
I didn't tell you to look yet. No. And so let's see, but.
Man, Nathaniel's up on.
Actually, I think I'm going to do this because it's an array, right? And so I'm going to use my array hack because I know that.
What?
Talk to chat. I got to make mistakes and think it through. And I know this is not right yet. I'm not there yet. Hold on. All right. So actually what I need to do here is because. Right. So hold on. So at some point I'm going to need this, which is replacement for that because it's this instead of this. And here's the thing, though. Here's the thing, is that we can, so an array is just technically a pointer to the first element, a pointer to the first element in that array.
Mm-hmm.
And so I'm setting that this is an array of 5 characters, and then I am casting, but technically what this actually is a memory. This is a pointer to the first element in the array. Okay. So it's already a pointer. So it's okay. It's just the same thing I was doing before because it's an array and arrays are weird. And so then with the other thing here, I'm just casting it that instead of being a pointer, I don't know if I need to cast it. It kind of already is. I do because emalloc is going to be giving me a void pointer. So I need to cast that to be, I think, a character. That would make sense because it's a pointer to the first character in the array, so it would be a character pointer. So that's okay. And then I can copy that into this, which technically is a pointer, but it handles it okay because I've done this before. Okay, all right, you can look at it.
I'm not saying anything. Okay.
I love that. I have to work through things sometimes. And it means
no, it's totally fine. It's totally fine. But I have a lot to say about this, and I'm not saying anything.
All right, so let me at least walk you through. I don't think it's right, but I'm not really sure where it's wrong.
Okay.
But let me kind of walk you through my thought process here.
Okay.
So.
I love line 32, by the way.
Oh no. Okay.
I like what's going on in line 32.
No, line 32 is wrong. Line 32 is wrong.
It's slightly wrong.
It's slightly wrong.
It's not all wrong. Yep. That's looking good. That's what we want to ask for. And no,
Okay.
spaces are fine. We don't need to be,
I like my spaces. All right, I really do. It
Okay.
helps me read it. Okay, so right. So with care other thing, 5. My thought process here is that when we learned about arrays, pardon me, I remember you telling me that some of the weirdness with using pointers and arrays arises from the fact that technically the variable that we set to be the array is actually a pointer to the first
That's
element.
true, but that's syntactic sugar. Right now, we actually want a pointer, which is going to go to the first thing in the array. What is this allocation we have on 31? What are we declaring on line 31? I mean, I know the comment says we're declaring a pointer to the first element of the array, but the compiler doesn't read the comment.
Technically what this is it's an array of 5 characters.
Yes, that's correct. And that's the problem.
So then if you want me to be explicit and there's like no syntactic sugar allowed, give me 1 second because I actually think I know what to do. So here, hold on, we need the address of operator.
Wait.
Right? So what I'm saying is we need the pointer to the first element of the array, which
that would probably work, but that's some evil C you just wrote. So let's take a step back. We want a care pointer, which is going to point to this dynamically allocated array. Now, before we changed what was happening on 32, which I mostly liked what was happening on line 32, other thing is going to get a casted care pointer. We're going to take the void pointer, we're going to cast it to care pointer of emalloc of size of care times 5. So if our memory allocator works fine, that's 5 bytes. And the address of the first byte is going to be returned in other thing. Except other thing is not a pointer. It's a array of 5 that you're referring to the pointer of the first address.
Technically arrays are just pointers to the first element.
That's true, but it's a little evil. Why don't we make this a real pointer?
Wait, okay, so before you do what you can I ask you, why wouldn't this? I know you said it's evil C, but I'm really not sure why that would
evil. Yeah, no, it probably would work.
So
actually, it probably would work, but it's evil.
It's very explicit.
No, because
give me the address of the first element and set that equal to
which is a pointer to that array. But the problem is that you're talking about stack memory here. You're then going to overwrite that pointer. You're not going to point to the array anymore, which is probably going to cause the compiler to freak out at you with a modern compiler. And you're going to go point. You're going to go point it to somewhere else. That emalloc is going to be giving you out a chunk. So let's just treat this like what it is.
I see what you're saying.
Which is a real pointer.
I just want to make sure I'm following you. So the way that I had done it, so really quick before you fix it, because I think I see what you're saying. When we do it like this, the problem is that we're initializing this in stack memory, which has its own memory address. Then we're kind of saying, take the memory address of this thing and stack and wait.
Let's go overwrite that type. So I mean, we might compiler. If the compiler's not very smart, it'll work just fine because it'll go fine. That's a pointer. But
I see what you're saying. Okay, so I guess my issue with this was we here is a pointer, a care pointer. Fine, we're well off and good here, and we can this should be fine then.
Yes.
We don't. Okay, I see my problem. I was really worried about somehow needing like. Okay, I'm goofed with the arrays. I was really worried about it, like knowing that this was a pointer to an array of a certain dimension, but that's taken care of right here.
I had to go to duct tape. Okay, I want you to know that I had to go to duct tape for this, like, because I was like biting my tongue on that one, like, that's
how people learn, though. Like, you gotta allow for the experimentation, right? Okay, so.
Nathaniel, I think she had she leaked memory the other day. That wasn't a buffer overrun, but let's kind of see what happens. Let's
out of chonk. Yes. Erzrig. See, here's the thing is that like programmer. So
I love Erzrig.
of the future, 2,000 years from now, are going to be like, what is like the, etymology of using chonk to mean like, this pool of memory, and it will trace back here. All right. You've heard it first here.
Well, the funny thing is that a lot of these things use thunk allocators. But I'm trying to resist like getting into that. That's why I was trying to use the right term about pool. But anyway, we'll get to thunks
We're gonna
later.
have fun, and I promise I will remember that it's pool when I am writing the first pass often or learning.
Don't make promises you can't keep. All right. Anyway,
I can remember. Trust me.
Okay.
Okay.
So care pointer, we point it to emalloc, we get a result. Hopefully 5 bytes. We assume that we always got memory because memory never runs out, even though we now know exactly when memory is going to run out because we've written our own allocator.
Well, so this gets back to like this assert idea. Like I know you said
No
we're not
assert.
going to do that because it's debugging,
Yep.
right? But I really want to put something else in here. But I thought you would say no, that's like debugging, and
Yeah.
But okay.
No asserts. Yeah, definitely no asserts.
Okay, fine. Can I say, because I really want to put like a...
Oh, you could write warnings if you feel like it. I mean, that's that.
It's that if chonk index plus size is less than or equal to, oopsies, is less than or equal to 2048.
Wait, no magic numbers. No magic numbers. What is another way to
Is
refer to
a
that? Yes.
chonk,
Thank you.
right? Oops, that's not right. And then this bit.
Otherwise, what?
I'm else. This is Python.
That Python.
Right, that's what I do all day. All right.
Oh, sadness.
Right, because we need to make sure that, like, I know.
Except this is a well-defined interface. We have to do exactly what malloc does on the interface. We don't get to change the interface.
I'm not changing the interface. It's returning its voidness. It's taking its whatever.
Now you're not returning anything in that case.
The capitalized, I feel like going
Oh,
like,
man.
really angry.
Erzrig just gave you the best thing. It was such a missed opportunity.
Out of chonk. Oh
Out of chonk!
Oh,
No Dutch caffeine, naughty. By the way, Dutch caffeine, to your earlier question, this is we're learning C as an additional language. Jessie is a Python programmer, astrophysicist, and she does various things and wanted to learn some C, so we're doing some C. And what better way to really get into C than to build your own memory allocator? And by the way, they were asking, Erzrig was asking what the equation is on your whiteboard.
So that is the equation for reinforcement learning. And so if you want to add that to our Scotch discussion for later, I love talking about reinforcement learning.
Okay,
I think
I'll
it's
pin
the
it.
future of machine learning. And so we can talk about it then, but I also don't want to take away from the chonk.
Yeah, we got to finish our...
Will you let me do something?
Yes.
Will you let me do something? Okay.
Just don't change the interface of malloc. Don't change the interface. Okay. I don't even know what I'm looking at.
He doesn't see it. Don't tell him.
What?
You don't see anything. You don't see anything.
What? What? There's a scrolling bug in this thing. Chonk alloc? Okay, fine.
We can call it Shallock.
Chonk Alex, great. I love Chunk Alex. Let's
This is awesome.
let's go with that. All right, you're allowed to change the name of it, but you're not allowed to change its.
I didn't change anything else.
You're not allowed to change its interface. It has to be the same interface.
It was Sunny's comment about this better replace gem malloc, and I was like, wait, this is e-alloc. That's such a terrible name for something that's so chonkalicious.
Yeah.
Okay, so
Chonkalicious.
I wanted to put a safeguard in there in case we reached the end of chunk.
Dutch
Right?
caffeine. That's because we're building malloc. We were using malloc, and so this whole project is about understanding what malloc does and
Yeah.
rebuilding it. So we're keeping backwards compatibility, and we're not allowed to change the interface because Jesse has been trying to change the interface on us a few times, but you don't get to do that a lot in programming. You have to deal with a legacy interface, and you could do any sort of magic you want in the routine as long as you conform to the interface.
With compatibly as a support Windows MB.
Yeah. Well, this is malloc. We're supporting all the way back to like the 1970s here, so there's quite a story on this one. But
okay. So now at least I wanted to put like a safeguard in there, but then we had this conversation about exit 0 should solve the problem. I don't know what that means.
No, that's a troll. I mean,
Okay.
He's basically saying you just quit the program.
I would like, but
You don't get to quit the program. That's changing malloc.
I returned null. So
yeah, you returned the right thing. Malloc
Okay.
returns null.
Is there a null pointer? Do I need to have a pointer since it says it
Null
specifies
is
that
its
here I
own
return a
pointer. It's zero. Does 0 have units?
No, the reason why I'm asking is because in our definition of
That's
the function, it
philosophical.
specifies what it's going to return. So I didn't know if there was like a pointer that I needed to return here for this.
Yeah, but null will turn into a pointer here. That's because it's memory address 0 if you interpret null as a pointer.
Okay, so it's just like no.
Yeah.
All right.
Yeah, like if you get into C++, they're actually distinct. There is a null PTR thing, and anyway, C does not differ. It's actually it's the number 0.
Okay. Yeah, I just wanted to be like, nah, like you messed up.
Yep, and you dereference a null pointer when you try to dereference 0. Okay, so we have some confidence that our implementation is correct, right? Yeah, how do we get more confidence? How do we know that we got this right?
You try it, you see what happens.
Why don't we starve it a little bit? Let's have a little fun. Let's look at all this memory you've got.
Oh, tiny chunks.
Now, there was a reason I kept telling you don't go littering your 2048s all through your code because
Fair enough.
we're going to go.
Be able to
2048 is not a realistic numbers, and our program shouldn't care, right? It should be correct no matter what the size is. Okay, so if we give you only 3 bytes, what are we going to do?
Well, hopefully we'll get the out of chunk error message.
Yeah.
Let's find out.
Hey, segmentation fault. I love it.
So I want to figure it out. So hold on. So, ooh, this is weird. It's like cutting off. Can you read the output? Like my browser's being a little bit weird. Oh no, here we go. I got it. Okay. So it does the first thing, right? And we expect it to fail. But it fails in a way that I'm not expecting, which is that, okay, warning format, this is a char star, but argument 2. Oh, this is like that weird, hold on. So this is, because this is left over from this, which is that this needs to be, hold on, address of operator, dereference operator. That needs to be this, I believe.
I'm sorry, I missed which line you changed.
41. Okay. So I think that here I was changing I was trying to copy the string that is my name into the pointer, which doesn't make sense. So I need to be copying it actually into the thing that it points to.
No, it was right. Because stir copy actually takes a pointer. So yeah, no, that was right. That wasn't the bug. In fact,
I see the segmentation fault, but before that, there is this error on, like, a formatting error saying something having to do with my %s.
Wait, that's line 44.
But it says, look, warning format,
yeah, I'm looking.
%s expects our argument of type char star. So it expects a pointer. So that char pointer, but argument 2 as type int. So
yeah, other thing is a string. So don't change the type of the output. It's supposed to be a string, right? So
I think that might have fixed it.
No,
yep, that fixed it.
Well, yeah, I mean that was the warning, but
no, but it took away the other problem. I was fixing errors one at a time, and so this fixed the first error, but then this error.
Yeah, we seg faulted. We don't have that memory, which is actually what would happen if we didn't check the return type on malloc, right?
Mm-hmm.
I mean, if malloc returned null, which how do we know in this program if it returned null?
Mm-hmm.
So let's look.
So is the problem that because it returns null, later when we try to, but why is it still not, it's not giving the error message? So I'm guessing that, chonk index plus size is much smaller than 3, right? And so the problem here being, so hold on. So this should trigger because this condition is met. And then, or sorry, not this. This should trigger because chonk index plus size is not less than or equal to the size of chonk. And so it should print this and return null. We should at least get that print. Even if we get like a fault later, we should get the print, but we don't. And so that makes me think that it's somehow this condition is being met. So I've written it wrong.
Sunny,
somehow.
what are you posting image links in the channel?
So chonk index, every time we run this, it should set 0.
Nice.
And so it should initialize. It should clear the memory that we're interested in. Chonk index should be 0. And then 0 plus the size in the first one. I mean, it should fail with the first one.
Oh, I just didn't know, Sunny. That's why.
So it's failing with the first one. So then
wait, why don't we see how far we got? Let's do some printf debugging because we're not allowed to use the debugger yet.
So hold on. If this is met, I want to see if this is what it is.
Let's new line so that we make sure we flush.
Oh yeah, thank you. Okay, good. So this is not met.
Let's see if we. Let's get back to a positive case because right now we don't know what's failing. So start right at the top of chonk alloc. How do we know the error's there? Yeah, right now we don't know where it's failing.
So it's not even starting. So hold on. So it's got to be something here. This shouldn't cause. Oh my lord. This shouldn't. Right. That's just a pointer. That's fine.
Well.
So this is where. Let's see.
Oh, it's not updating? Did we lose the stream?
I'm watching stream.
Okay.
It looks like it's updating.
Oh, the seg fault's happening over here, everybody. She just cleared it. So here we're. Yeah.
So we're not even getting here.
Yeah, so we can't even really trust printf is what we're getting at.
Yeah.
So, and this is one of those like early init things. So anyway, we know something bad is happening. We know that our program isn't dealing with it. Let's assume that we get through the first allocation. So I'm going to give you the 4 bytes. Well, you know what? I'll give you 8 bytes. So let's just see if that starts giving us some output. No,
because this is much bigger. I need much more because this is an int. So don't we need? No, we should be able to get that.
no, that should fit. Well, here we'll give it 10. Okay, so something funky's happening.
Hold on, let me clear this and run this again. Sorry. Okay, so
The rest
beginning
seems
here.
static. Yeah, maybe there's a problem with the OBS has really been acting up tonight.
This seems static aside from the mouse. Oh no.
Yeah,
I do see that. Yeah.
Yeah, when I change the
So we can save it and try to refresh.
Yeah, why don't you save it? Hopefully I don't have to rebuild that again.
I'm just gonna copy it just in case. All right, chat. I have refreshed it.
Yeah, it is definitely. All right, I'll set it to that. Set it to that. Okay. Hopefully that is updating now. Yeah. Yeah, okay, cool. Yeah, OBS is not liking focal. I just went to a new version of Ubuntu and they're...
We are out of sync. So at least according to, I'm like watching, you have output there, and I've cleared it, and I refreshed.
So gotcha. All right, let me refresh. Well. Sorry. All right, so now when I do this...
yes, okay. Now do some spaces or something so I know that we're in sync. Yeah. Okay, I see you editing. Okay. Yes, we're good. Okay. All right.
So, cool.
Yes, very good.
Sorry about that, everyone.
All right. Okay, so... Right,
more
so
seg faults, please. Okay, they want the seg faults back. We got to give them the seg faults.
We're working on it. Okay, we're working on it. So
let's starve the memory again. All right, so we're back to 3 bytes, and hey, there we go. There's your seg fault. I love that the stream screwed up as soon as we seg faulted. That makes me happy in some deep part.
Okay, so I think the interesting thing to me is that it's happening. I put a print statement like basically right here, line 37 in main. I put a print statement there and it didn't print out.
Right.
So it's almost like somehow when you set it to 3.
So when we made it 4, it
breaks.
failed 2.
Yeah.
And when we made it 8, it failed 2. And when we made it 10, it worked. But let's try 9. Oh, okay. So that seems to be the byte. So something seems to be going wrong with that first move, or something after. I mean, so we know that here's chunk. What are all our references to chunk? So changing chunk seems to be what's causing trouble. So we can look at chunk index. It starts off 0. That's nothing can go wrong with that. And chunk initialize starts off at 0. Nothing can go wrong with that. So the only real action is sort of starting down here. So we have this other thing, and other thing is an int pointer, which comes back from here. And then what do? Now we know that's bad in the case that chunk alloc returns null.
Yeah, exactly.
Okay, but we're assuming that the output is ordered, that the output is making it out before the crash happens.
The output is making it out before the crash happens. You're assuming the null. Well, so that's why I put
so we're assuming
here.
We see that printf.
It shouldn't even try to return. But wait, okay, hold on. So I have a question. So before, when everybody was kind of laughing about like null, you said that it's a pointer to the null, like to 0.
Yep.
Right?
Well, it's just 0. It's null is the number 0.
The problem is that we need it to not, like, I understand that, okay, the syntax or whatever, the system, I forget the word you used, requires that we return a pointer. I get that. The problem is that if we return a point, I don't know why the printf isn't working, but that is it trying to grab a piece of memory that starts at 0, the 0th place in memory.
Let's not, and then it's trying to write something into it.
It's writing to it, which is the problem. But it needs to, we need it to like return basically not a pointer.
No, it's got to return null because that's what malloc does. So
but why isn't it printing at least?
No, that's what I was addressing. So I was saying that we're assuming that we see the output before the program crashes.
Well, before it even returns null, it should print, right? That's just like how the code is written.
Do we know that the output makes it out before the crash happens?
So, I mean, the only other way that is that somehow printing this crashes it, or our initialization crashes it, or like we don't even get this.
Wait.
We don't even get the beginning chunk alloc. So it's not even initialized. Something else is
We
is
know
this.
For a fact that this line is bad.
Yeah.
Like we know that if it executes line 38, it's going to crash hard.
Yeah.
Now the question is, do we see the output before that crash happens or not? Do we know?
No,
well, right now we don't see the output, but we don't know if C is going to give us that output or not. We do know that when we give it enough memory, it works just fine.
But the question is like,
And we see all the output.
why would we not? We don't even get, even if I put at the very
Before we
beginning
say
of
why,
a print statement, it still doesn't run that.
Wait, before we say why don't we try to test what's actually happening? Because we don't know what it's doing right now. Like, by definition, we don't know what it's doing right now. It just says it's a segmentation fault. We don't know when it happened.
Okay.
All right, so let's start with if other thing is null, then something bad happened. Let's just stop execution. We'll throw an error. How's that sound?
Sure.
All right. We run it. Now, this is fine because, okay, well, exit, you're supposed to add in standard lib. So I'm going to fix my code and add in standard lib. And so now we have standard lib. Execute this thing. And now this was fine because we had enough memory, but when we had not enough memory, look at that.
That doesn't make any sense.
It wasn't about making sense. It was about what is the computer doing.
Yeah, I have no idea.
Making sense is a very human concept. Like, C is just giving you the tools. Like, it's kind of like what it does is a little bit undefined when you get a segmentation fault. So what's actually happening here is you're actually getting a race between printf, which is trying to give you the output in the right order, but that's a buffered IO stream, and the program is crashing. So if the output doesn't escape before the program crashes, you're just going to see the segmentation fault.
I guess that doesn't make any sense to me because I feel like, so that implies that it's not running things line by line.
It is running them line by line, except that this is sort of a leaky abstraction because printf does not actually print at the exact moment that it's called.
That seems kind of useless.
Well, it basically, it's telling the kernel, like, I want you to write this thing. I mean, there's a bunch of
like
printf
when you
kind
get
of stuff.
to it, write this thing?
Well, it does some formatting stuff, and after it's done its formatting stuff, it then says to the kernel, okay, I want you to send this to the standard output stream. And then the standard output stream is supposed to take its little time and send the thing out to output. Now, because that's a system call, it depends how it's implemented, but because that's usually a system call, like, your program's crashing before that output is getting out there.
But I guess to me, that seems like really bad design for printf.
Well, maybe kernels. I don't know. I mean, it's just.
I mean, what's the point of having printf if it's not going to print when you tell it to?
So because printf tries to print in sort of an efficient manner. It doesn't stop it doesn't stop the world to make sure that made it out. In order to do that, you have to use what they're mentioning in chat. There's something called flush. You need to flush the output, and that literally says, "Do not continue until this thing has made it out."
Yeah, I like that. That's kind of like the assert, right?
Yep.
Yeah. That's what I wanted to use earlier.
Okay, you can, except it's not assert. Assert is very different. That's
it's not the same, but it's like a similar concept that, like, you do not pass go unless a certain thing is done.
Okay, so.
Right? Which is, like, very useful. Those kind of gates are very useful because then you can, like, scatter them throughout and really sort of narrow in on what's going wrong. Right?
Yeah.
Especially if, like, printf is not something that kind of is
I let you struggle with this for a reason. C does not always tell you what it's doing. Okay, like in particular, you don't know exactly. It's not that C is pretty literal, but you don't know exactly what the system is going to be doing under you. You know, like you don't know exactly what this library does. Like, you don't know that the assumption is hard that this stream has to be flushed before it continues or not. Right? That's it. Probably it might say that in the man page. It might not. I mean, I'm not 100% sure. Like, getting used to buffered IO, like, this is kind of a common pattern. It was done for efficiency, like, so it sort of like tries to like buffer up a bunch of memory and then flush it all at once so that way, like, it's efficient on, the way calls work. And this gets into an old, like, 1,000 bytes writing 1,000 times versus writing one write that's 1,000 bytes. The one write that's 1,000 bytes is a lot faster. So this kind of gets into the world of buffered IO, but it should be a hidden implementation detail. It's not here. So in this case, your segmentation fault, despite occurring above, is eating you not in the order you expect. It's not running it out of order, but in this case, like the printf is like, it's being passed off to the system, which may or may not have sent that. Like printf doesn't guarantee that it immediately came out. Flush does that.
I like this flush thing then.
Yeah, like you have to flush it to actually, and this is, flush says like I want, that's the link. So
I'm making a note of that. Sorry, I like this thing.
Here, I'll pass you the, this is the actual call. I just pulled it out of the manual page, and flush does do that, right? So you pass it a stream and it will, flush that stream, and it will not continue until that stream is flushed. So that does guarantee your sort of ordering.
How would you use that? I'm sorry. So it takes a file?
Yeah.
So.
Yeah, you can flush any file, including standard out. So, which is
I see.
Usually, I mean, it depends how it's defined. If it's one of those like.
Can you kind of show me how you would use it in this case? Because I'm still not sure what you mean by.
In stdio, you actually get this definition. So this, in the current version of C that you're using, standard out is defined as a file pointer, right? So it's actually, when you're printfing, you're just printfing to standard out.
And that's a file?
Yeah, it's just a file. It's treated as a stream like anything else. Before we treated them separately when we were first learning, but actually they're not. It's file semantics. And just the same way with file semantics, how we don't know if something was written to disk, because the program execution will kind of keep going, like, because disks are slow. Why do you want to wait for it? Unless you really care about it. It's like, no, I need to know that this happened before I keep going. Like, for example, when I save, if I do a save, I want to flush that file. I want to make sure that it's saved before I keep going. I don't want to keep executing and potentially crash and the save is like screwed up. Mm-hmm. Okay, so I can flush that, right? And then I will see it. So I could just flush standard out. I don't really care about the return value in this case. I just need to know that flush happened. So I could throw an flush in there and it'll happen. And now I can remove my check that I added before, and I run it, and this time
we get the
output because we were guaranteed it. We said no, you don't keep going until that thing makes it out. So despite the fact the seg fault happens, and that's it's mixing up the output because I'm printing standard error before I'm printing standard out. That's an implementation detail of mine, but that's pretty much what happened.
So is there a way then that I could build that into the definition of chunk alloc that we sort of like, because I guess the print statements aren't super great in the sense that it's going to like return this null or whatever, and it's still going to continue and it's going to break before it can print it. Is there some way that
that's how real malloc works, by the way?
The forced flush into it.
No, but that's exactly what real malloc does.
Well, what if we make better malloc?
Okay, well, chunk alloc can do that. So, all right.
Exactly.
Yeah, go ahead. You can add the flush.
Can we do that like in the else somehow so that it like knows, okay, you need to print this before you even move on?
Sure. And by the way, that's what Urzrig is like your
yay! See, we are
your soul partner here.
Yes. my code soul.
Oh, right, sorry, chat ran away. I'm sorry, chat. I missed that. We were getting into some debugging.
Not print up. I was reading chat and just writing things.
Yeah, Nathaniel knew right away about flush. That surprises me not at all. What should malloc 0 return? Sonny, you're trolling me. That's just it's one of those fun philosophical debates. Like, there's a great bit in like the BSD man page about it, which is like malloc 0 returns 0 because it's a dumb answer to a dumb question. like they actually, I forgot exactly how they worded it, but let me see. It might be in Linux man page too. It was, yeah, it's always no, they don't have it in this one. I think it's in the BSD manual pages, but anyway, it was a fun one. The new line doesn't. It should flush, but it doesn't always flush. I'm not sure if she had the new line in there or not, Jay. Performance, if you flush every time, Nathaniel's correct. Yeah, there's a small performance hit to adding flush, which is why it's not. That's why printf doesn't flush by default, by the way. It's about performance. Harris Studios, no, this is not her first programming language. She's been in Python for a while. Oh, sorry, you already answered that.
Yeah, no.
And Malloc of Malloc. Evil Brenner.
Ooh, nested Malloc.
Yeah, don't do that. Okay.
Yeah, that sounds like a bad time.
All right. So great. That's that there's a little bit of torture for you. That's the fun of real C.
No, I mean that's really good to know, because I think
that's why I didn't want to skip
folks
past it, because this is something where like it's confusing. You're like, no, why is it not printing my thing? It's like, well, guess what?
It's kind of interesting, because I just
it's a leaky abstraction in this case, because it. Oh, and thanks for the follow, by the way, Ursrig. It's a leaky abstraction because it requires knowledge of buffered I/O, but it is probably there in the manual pages. I mean, it's just one of those things. And Harris Studios giving you the feels, because it would have been pretty brutal to start with C. I absolutely agree. I
mean, but at a certain point, though, like, yes, it's brutal to start with C, but then at a certain point, not brutal, I think that's a hard word, but like it almost becomes brutal to continue with Python.
I think Harris is not wrong.
So much for you under
under
the surface, that at a certain point, and this is where I hit and reached out some coding guy for figuring out, how to learn C, is that at a certain point you realize just how much is being done for you and how much that's kind of hampering your understanding of the deeper systems. And so as much as like we joke about C, and I love to tease about it being, a little bit obtuse sometimes, it's very helpful.
Well, even in our first conversation,
useful.
I said to Jess, like, I will teach you C so that you never use it. I mean, that was part of the comment. Like, it will make you a better dev, and there's no doubt. But it like I hope you don't generally use C. Like I try to write in as high level languages as I get away with when I can. But sometimes in Python it's not even
exactly like
that's true.
And so my background is not. I didn't have a formal computer science education, and so I really taught myself how to develop and everything. And so part of the problem, right, is like to Ursrig's point, is if you also don't know sort of like the formal education around programming, at a certain point you're going to have to step away from those like higher languages and learn the nitty-gritty stuff. I probably won't ever be a C developer, all right? Just putting it out there.
Don't say that. You could be. You never know.
Oh God. I will say this, so I think you'll appreciate this guy, but about 4 years ago, no, it had to be even less. 3 years ago, I literally remember saying to somebody, shoot me if I ever say I want to be a software developer. I hate programming. I hate it. It's the worst part of my job. And then literally fell in love with it. I'm like, oh my gosh.
Don't get into a discussion topic. I want to have bourbon if we're having a discussion topic.
Okay, all right. It was just a quick anecdote.
We only did half of our task. We didn't get to free yet.
Okay, all right.
So, by the way, Brenner, I wouldn't say that I disagree. I would agree. That's exactly what I'm saying. I think that C is a great language to learn when you really want to know how the computer works. I mean, assembly is even better, but I feel like I think you got to get into all these things at some point.
Before we do free, you answer chat. I'm going to use the bathroom real quick.
Okay. So basically to that, I don't think that it's to some sense, I still think that C is a great rite of passage to a developer, that's especially coming from just higher level languages, because so many of the details are just sort of done for you. And that's good because you're usually thinking about your algorithm or your data set or whatever you're actually trying to get done. But on the flip side, it also that level of abstraction can sometimes blind you, because it just leaves you in you're not really sure how a lot of this stuff works. So you don't necessarily know when you're making crazy assumptions on the computer because of how you wrote in the high level language. So I really do think that there's something to be said for C as sort of a reasonable abstraction over assembly, and then assembly just because, at some point I think you got to know. Not that you're going to be writing a lot of assembly, but not saying an enterprise application in C, just so I understand that it's under the hood when they program, teaches you good habits. Yeah, I mean, I've also seen a lot of bad habits too in C, by the way, but I think you should either learn x86-64 or some type of RISC assembly, just enough to know. Yeah, I agree, Nathaniel. I would even pick something simpler RISC being, it depends which RISC, but I mean, something like 6502 I think is fairly ideal. It's not RISC, but it's sort of there's not a lot of registers. It's relatively easy. And x86 64, there's so many like the complexity's really high. Not that I think it's a waste of time, but it's almost a bit more advanced these days. I mean, I think like even like old school x86 is probably, better as a learning language, but or something like PIC, which got brought up last week, and I went and bought a development board, but I don't see the PIC people here tonight. But this is another fun kind of assembly world. There was I really like the RISC-V stuff that's been kind of going around. It's not licensed or anything like that. Erzrig wrote assembly for a living for 10 years. Wow. Give Erzrig a drink, please. Assembly, COBOL, and Fortran. Yeah, I mean, it depends. Like, coding's coding. They're all Turing complete. I'm not going to go choosing to write stuff in like COBOL or Fortran. Well, Fortran's not that bad, but I mean, it's not going to be my first choice for like a web thing. It seems like reviewing non-optimized assembly that your C compiler generates is just as valuable. That's true too, Josh. 68K. Yeah, 68K was, I think, my first assembly. No, that's not true. I had that TI 99-4A with a crappy non-6502. I like lots of registers. I like AVR assembly, MIPS. I mean, these days I would go with RISC-V just because why license? And there's reasonable tool chains available now. So this was from the implementation I did in JavaScript for a previous stream. But the instruction set's nice and compact, and still learnable. Like you can reason about the idea is to reason about what's going on, and still it scales. Is that web app you're using in Node, I'm assuming? No, it's in Python. I wrote it. It's actually open source. It needs a lot of work, but I wrote it for these sessions so that we could get coding and see the same screen. There was not a lot of stuff that was available that was like didn't have like licensing or signups or guiltware or whatever. I would argue if you get into free diving, you don't get thrown into the deep end of the sea. If you survive, you survive. You should start in the swimming pool. Yeah, I mean, I kind of agree to Harris Studios, and I think that's a nice approach. It's coming from something like Python to C as opposed to like doing C and then going to Python. Makes you don't want my take on Python. Yeah, we can get into that during. We'll have some bourbon before we get into that.
Yeah,
all right.
I'll need a glass of scotch. All right.
Let's finish up. Let's do our free real quick.
I was thinking about the free.
I was going to have one reach task, which was because your free is basically free. I was waiting to do it. No, I didn't. I just thought it up. But free, because your free was waiting to like it. There's relatively nothing in the implementation. I thought it would be more fun for us to try.
I was just going to ask you that. So
you were asking about malloc and how do I know if I allocated memory or not? And so I thought it'd be really interesting to add exactly what you asked for, which is like, how can we trace allocations? Because when we have our own allocator, we can actually...
What do you mean by, I'm sorry, trace allocations?
Well, we can tell whether you gave back all the memory. Remember before, the first time you used malloc, you leaked memory. Mm-hmm. And it didn't tell you, right? Because there was no crash there. It just, the process shut down and everything was fine. And I said, yeah, you had your first memory leak. Well, with your own allocator, and even some professional allocators, you can actually trace allocations. You can say, like, did I give back all of the memory that I allocated? And one way we can do that is if we implement free, not actually returning the memory, but we just keep track of the statistics. So for right now, let's start with our implementation of free. So what's the interface of free?
I don't know.
Well, free, and what does it have to free?
I mean, so I'm guessing it's going to be another void.
Yep, doesn't return anything.
And
no, it doesn't return anything.
It doesn't?
Nope.
So
what's free's job? What does free do?
I mean, I thought things always have to return things in C.
Nope.
But I thought that's what we learned.
No.
Is that when you're defining a function, it always has to return something.
Yeah, and the return type can be void, which was our first use of the word void.
Okay.
Which is it always has to have a specifier, but the specifier can be, I'm not returning anything.
Okay, so this takes size, right?
Erzrig engraved chonk on a barrel. And yes, Jay, by the way,
engraved.
A lot of professional mallocs will allow you to trace. There's a bunch of tools, but
it's such a wonderful trick.
Jess is building her own allocator here, so she can trace her own allocations.
Okay. Malloc hooks. I haven't learned malloc hooks. Okay. So. All right. Okay.
What does free chunk have to do? Like, what's its job?
Okay. So it needs to keep track of. Ooh.
Well, first of all, you have the signature wrong because free is not. It doesn't take a size.
Well, in this case, we're actually not freeing anything. So actually
No. But the interface is that you have to tell it what it's going to free. The fact that we don't free it is an implementation detail.
Wait, sorry. Can you repeat that?
So
it's 10 p.m. My brain is like,
no, it's fine. The fact that our allocator doesn't actually reuse the memory is invisible to the user of this allocator, right? That's a detail for chunk and chunk people and team chunk, and that's it. Like, it's not a detail that's used by anybody who uses this library. So they think that this thing is going to reuse the memory, and later on, if we want to implement it to reuse the memory, we can, but we have to keep the same interface. We don't get to change the interface. Team chunk, man. Represent.
Lord. Okay. All right.
So what would it, regardless the implementation detail that we're not giving the memory back, what would it need to know?
I feel like it would need to know size, but it would also need to know the pointer to like the starting place.
Mm-hmm. That's what the free man page says.
Well, good for the free man page.
The free man page.
Let's give it the pointer to. But it could be any kind of pointers. It's gonna be a void pointer.
I'm gonna tell you right now. This is
I'm not.
This is straight out of the man page. Can't change the interface.
I know, but how does it know how much to free then?
Hey, party time.
Party time.
That's up to you.
Wait, no, but seriously, like
terrible Stropio.
If I ask for like 500 like chonk units and it gives me that, and then I free that, how does it know that it's supposed to free like 500 and not like 10?
Hold on.
I'm gonna make an entire operating system called Chonk OS, by the way.
Ursrig, please observe workplace safety with whatever you're engraving and playing with tools. Like, don't. You might laugh in this stream, okay? So don't lose a finger or anything because of what we're doing here today. So please either put the engraving down and just code with us, or please be careful.
Engrave chonk on everything. I'm in support of this.
Okay.
But no, in all seriousness though, how does it know how much memory to free?
How could it know? This is the interface. You don't get to change the interface. I'm mansplaining.
You said that, and I get that, but I'm also asking then, if all it takes is a pointer, presumably the one from the allocator, how does it know how much memory to free if it only has an address?
How could it know?
I don't know.
No, I mean,
that's why I'm asking you.
How do we answer your question? I mean, you're the one who wrote malloc, chunk malloc, chunk alloc.
Other than somehow recording, like
yes, you would have had to do the bookkeeping.
No, but that requires a I don't even know. There's apparently not C dictionaries, but that would have to require something like that.
I warned you up front. I warned you up front. This you are going to need some memory for bookkeeping.
I don't know. Why can't it just take size? It can. I don't.
Wait, you can't argue with the man page. It's the man page.
I can argue with whatever I want to argue with.
Okay.
I'm a millennial. I do that, please.
Okay.
No, but in all seriousness, though, right?
You wanted to learn C.
That seems so.
No, that's the interface. The idea here is that you are by adding size. That's something that you want to know, because in this routine, you want to build it so that it doesn't need to have any other information, right? Mm-hmm. Okay, but
and I get that that's a constraint. I'm just
no. But think about that. No. That's what you want as the implementer, right? Mm-hmm. You want that as the implementer. But who is going to use your implementation, and do they want to do that? Are they going to want to track the size as well?
Who's going to use CaaAL? I'm using CaaAL, so I'm making it for me.
And you're always going to want to do that even when the standard C library doesn't require it? I mean, which of these implementations is going to win?
I mean, so with the other one, though, I feel like it would be so much faster, to your point about speed earlier, to not have to record every single like size and memory address that I've ever like allocated in this particular instance.
Okay, but now you're making a new interface, like because you're changing the interface of free.
No, I understand I can't do that, but I'm also saying like it's going to be so much slower to have to record all of this information.
It's definitely going to add a little bit of performance. I mean, making it fast, again, we're aiming for correctness.
And see, Erzwig has a perfect point, okay? One has usability, the other has chunk.
So I'll use chunk. Okay. You might win on just chunk, but the reality is that's an implementation detail that most developers are not going to care to track because they're just not going to use your libraries, the reality. And that's how a lot of this stuff got chosen in the first place. It's like, okay, this one was easier to use than that one, so I ended up using this one, like that technology won. Like, why did this interface?
Programmers seem to love to like everything to be like laboriously detailed and like have control over everything.
But they do,
you want
right?
Exact control over what
they do have that, right? If they want to build their own memory allocator, they can. Mm-hmm. Just like you're doing right now. I mean, they have exactly that choice. So this was about like what was a reasonable like standard option, that people wanted to use. Oh, and see you later, Dutch Caffeine. Thanks for dropping by.
Because we also haven't really, I guess it would have to be an array, but like we haven't really learned if there's any kind of like dictionary-esque sort of like keys and value association data type. And I guess we could make a structure, but like
we could. Wait, but before you get into the implementation of that, right now your free chunk doesn't have to. What does it have to do, based on our initial constraints?
Well, because we don't really need something to actually free the memory. Mm-hmm. We just want to. You said something about like keeping statistics.
Okay, so before we add the keeping statistics constraint. Here's your implementation. I'm going to write your implementation of free chunk. I thought this was one that you wanted to write, but I'm going to write it for you. You ready?
Mm-hmm.
Done.
What? That's a trick.
What do you mean it's a trick?
You said that we needed to like keep track of statistics and stuff.
No, that's what we were adding on later. But in the original version, that's just to make it more fun, is we're going to add statistics. But to meet the interface requirements, what do we have to do?
We don't really need it, right?
Yeah, we don't need statistics are not part of the interface requirements. That's part of our that's a reach goal. But our actual implementation, that's it.
Okay.
That's
it. This feels like one of those physics problems.
You want to test the free chunk? I don't know. Let's see if it works.
Okay.
First of all, you didn't add you don't have the exact interface, so I'll take some points off for that. But
free chunk, and then we'll hand it. Hold on. So this is the. I keep swapping them still in my head.
But be careful about that, Erzrig, because we don't know that the user didn't write a 0 in there. So we can't use 0. We can't use a pill to signify that is the end of the allocation. It's like the intuition she's going on is right, that you would need to trace the allocation in some fashion. Or you would need to, if you don't want to use a separate structure, you could actually just arrange your data structure so that there's always like some bookkeeping plus the memory plus some bookkeeping plus the memory, so on and so on. It would be nice with a map, as Strophium's sort of mentioning, but we don't get a map in default C. Oh, Erzrig was adding on to Strophium. I'm sorry about that, Erzrig. I missed that. I'm a little behind in chat. I think I'm watching the stream. Thanks, Harris, for dropping by. Here I thought we went through the hard part with the malloc and we'd do the nice easy part. That'd be a nice gimme, but you just didn't want the gimme. And yes, Nathaniel's right. Strophium's right. A map would be ideal. We don't have a map. So we don't get that in default C. So
What do you mean by a map? I'm sorry.
A map is
that a data type in C or something?
No, this is you get the it's a dict in Python.
Okay, it's a dictionary.
Yeah.
All right.
That's an unordered map as opposed to a ordered. I mean, it depends which language, Map is an overloaded word. Using the Java definition, it's really just an interface, and it could be a hash map underneath. It could be an array map. It could be whatever. It's just one of those things. But yeah, moral of the story is that it's key value. It's somehow related. It doesn't talk. Map is non-specific. When you use the word map, you're being non-specific about the implementation, which is what I like.
So Harry Studios has a really good question. And I know we're learning C, not C++, but like for a buffer that you call delete, how does it know how big the buffer is?
C++ is not this stream.
That's an interesting question, right? Like to learn, well, here's how C does it, but also here's how other languages tackle the same problem.
I'm interested first in how Jess does it because, we haven't gotten to your
Apparently
implementation.
Apparently I'm cheating and it's just like an empty... I'm telling you, that's what I was telling Ursula, is I'm going to make Chonk OS. It's beautiful.
OS.